Hello everyone, we are 666. In our Pacman game project, we are using multi-color tree search and approximate Q-learning function, and let my teammate to introduce them.
The basic structure of the agent strategy is multicolor tree search, one of the online planning methods. The search is done while the agent is executing. Every time when the agent visits a new state, the multicolor tree search method will be invoked. Then the Q value of each possible action from the state is computed. The algorithm simply follows a bit-first strategy at a stage, chooses the maximum Q value among them and updates the simulated value. Then a search tree is built. In this project, we limit the search depth to 3 to make a balance between the efficiency and the effectivity. To simplify the state, the approximate Q function method has been applied to the algorithm. Instead of recording all information for the game state, some important features are chosen to present the state. For each feature, a weight is assigned. Unlike the Q-learning method, the weight is not learned during the execution, but assigned depending on the agent status. With the feature and the corresponding weight, the Q value of the state is a simple linear combination of the feature and weight. The Q value is used during the simulation process. So of the challenge part, for attacker, during the testing process, we found that sometimes the agent may be trapped and keep repeating some meaningless action until there's a ghost nearby. Another potential problem is that when the nearby ghost is scared, the agent always ignores it and even try to run away from the ghost. The scare time will be wasted. For defender, the defender always waits at the boundary and ignores the capture. It will fall to stop the enemy agent if the capture is eaten. So the improvement is that set more proper weight. The weight have significant influence on agent performance. And the next one is set a timer to monitor whether the agent is trapped. And the final one is set a strategy. If the agent has earned enough points which can ensure our victory, the attacker agent will no longer attack actions. Instead, it will return home and defend our own food. Approximate Q-learning function is based on Q-learning, which is kind of reinforcement learning technique. As a model for algorithm, Q-learning guides the agent learn the policy based on reward and Q function. To reduce the space complexity, instead of the Q table, we employ the approximate method. This method is to update weight each time for an optimal action. Through giving a positive or negative number as reward parameter to guide the agent eating dots or avoiding the enemy. So in design part, there are several kinds of reinforcement learning technique. According to the specification, the game does not have the stable state. The dynamic environment will result in policy change in each turn. So we decided to choose a policy free. Based on the description of the game, there are several 32 multiple 16 maps which contain packed dots, walls, and capsules. Comparing the approximate the Q function and calculate the exact Q table. Focus on Q table first. We need to store the state and Q value. Then in the game, the state may be a feature action, which means for each position there are almost 4 states. So the total number of the state is too large to use. Well, make the algorithm light, we decide to use approximate Q function, which doesn't need to store all table. According to the specific of the game, there are 2 Pacman of ghosts for each team. We need to attack the enemy and protect the packed dots in the area from the enemy. So we decide one agent is a defender, which is responsible for protecting the dots, and another is attacker, which is responsible for eating the dots of enemy. Well, the most challenge of the method is the way it's changing too fast and the difference is too large, which result we cannot find a group of parameters to guide the agent finally. The algorithm is need a large amount of training to help us to update and learning. We need to iteration the ways and do convergence finally in its turn to optimize weights to find the best Q value. In our method, we currently weights are not optimal.